Scott, if you're ready, I had you first on the list.
Yeah, hey, Chris, this is John. I think Scott is going to be joining us momentarily.
I see him. He just got on right now.
Okay.
Yeah, I'm here. Did you say you wanted me to go first, or I didn't catch that?
Yeah. If you don't, I believe I had you first on the list.
Oh yeah, you did. Okay. Well, good thing I finished.
So Scott's today is going to be talking to us about his synthesis report, which is about large wood management. So the floor is yours, Scott.
All right. Let me share my screen. Oops, turn that off. Is that working, Chris?
Yes, it is.
Hold on, my dog just opened the door. All right, lay down. And, okay. So, and you can hear me okay? All good?
Yep, you're perfect.
All right, well, I wouldn't go that far. I just want to first start off with some disclaimers. The first is that this was a project that Wes Smith was leading when he was working with National Marine Fisheries Service. And so Wes was kind of our cheerleader and organizer and putting all this together that I'll kind of give a summary about today. But he's no longer with NIMS, so I'm doing a kind of a fill-in for him just to kind of give an overview of kind of where he left it. And so I consider everything that I talk about today as a very preliminary draft that needs to kind of get picked back up again. That would include all the content in the document and certainly any kind of recommendations. And so I don't go into really any detail on recommendations because it hasn't really been vetted by the group that was working on this. And so when we go back to, I guess, the people that had been working on it, Aaron Martin and DJ were working with us on this at the very beginning. I helped out some, and John Baer did, and there's probably a few others that I'm missing. So I'm going to start off with just some background on this. As a flow study author, one of the things that we missed that we didn't spend a whole lot of time on was large wood management. So we talked obviously a lot about flow management and channel rehab and sediment management, but not a whole lot on large wood management. So over the years, we've kind of realized that that was kind of a missing piece that we needed to add in there. And so we've been doing large wood projects as part of our rehab projects, but we wanted to develop a large wood management strategy that would accompany, that could be pulled into the channel design guide as well. And so we didn't really have any specific recommendations in the flow study for doing channel rehabilitation for large wood, but it wasn't excluded either. So it was not a problem to add it in there from our perspective. So, and the large wood that's being done is obviously part of a larger portfolio for restoration in the Trinity River that really targets physical processes and cover for fry and juvenile cover, biological productivity and other functions in the river corridor. So the overall goals of the large wood management strategy, LWMS for short, is that we wanted to kind of shore up and put some more detail into large wood management on the Trinity River to support the overall record of decision objectives, so that the large wood management strategy was fully contained, conducive, in harmony with the record decision restoration approach and objectives, which it is, in my opinion. And that we wanted to also provide a framework for monitoring and assessment that would allow for both active and passive adaptive management. Because a lot of this wood management that we're doing is part of rehab projects. And it also provides a framework for regulatory compliance for projects. So I pulled a lot of the objectives out of the document, out of the draft document here. It's a lot of bullets. But basically what the document is trying to accomplish is, first of all, starting with a background of the role of large wood in other rivers that we can use as analogs, and a lot of these in the Pacific Northwest. Summarize anticipated benefits of this to the Trinity River, so why we would do this. So that's kind of the logical progression in the document as well. And provide the technical basis for including large wood management in the overall Trinity River restoration strategy and portfolio of actions that we're doing. And I think that's actually, it's a copy and paste, so it's a redundant bullet. Develop conceptual models of how large wood works in these kinds of systems for geomorphic and habitat functions. And then transition into developing vision, strategy, and augmentation recommendations that would include identifying large wood sources, storage areas, placement locations, and some other things I'll get into a little bit more detail. And then we would include this as an appendix to the channel design guide amongst the other appendices there that we can use for guidelines for large wood use in rehab projects, but also just other large wood implementation projects that may or may not be associated with individual rehab project sites. And then the monitoring assessment framework that's consistent with the record decision AEM process. And then also providing guidelines for managing risks and or impacts to infrastructure. And there are a number of them out there that we need to consider. So the draft strategy that we've developed, again, consistent with the ROD strategy, develop a future vision, treat large wood as a budget with routing, similar to how we do this in coarse sediment management. Implementation strategies, short and long-term augmentation, and developing guidelines for the types of large wood that would include species, sizes, density, and the minimizing risk that I already mentioned, monitoring and assessment. So Wes had pulled together from work done by Tim Abbey and Cardno Intrix and Rocco Fiore and Aaron, some nice historical photos that, just so you're not looking at bullets the whole time, that are included in the current document. That gives us kind of a historical perspective of how we think that large wood worked on the Trinity River. And these are early 1900 photos near Swift Creek, so underneath the Trinity Reservoir in kind of the broader alluvial valleys. And you can see a mixture of riparian vegetation along the channel margins, lots of conifers out in the floodplains and terraces, channel migration that's occurring, and large wood that's routing through here. There's active gold mining, obviously, has been occurring at this point for at least 50 plus years. So this isn't necessarily unimpaired conditions. There may have been a lot more wood in here prior to the gold mining period. But you can see a lot of these processes occurring here with large wood accumulations in the river in this kind of alluvial setting. And here's another photo under Trinity Reservoir, another alternate bar sequence with point bars and wood accumulation on the bars, riparian vegetation along the margins with some conifers out on other surfaces. And these terraces may have been cleared at one point, so there may have been more conifers and riparian out there. And then one last site here down at Valdor Gulch is below Lewiston, looking upstream, it looks like. So again, kind of a dynamic channel with riparian vegetation along the margins and upland vegetation up on top, and old meanders that are creating some large wood accumulations in these areas. And then lastly, more contemporary above the reservoir, near the Coffee Creek or at the Coffee Creek confluence. You can see there's probably a lot of large wood that's coming out of Coffee Creek, but it's accumulating on point bars as jams at the heads of the point bars, and then as well as growing medial bars perhaps here. So fair amount of large wood in the system, but probably still a lot less than there used to be in the system. So the way that the document's currently looking at this is as a large wood budget, where, and again, in a similar way to how we look at sediment budgets, where input minus output equals change in storage. And one of the things that the document's trying to do is to develop some storage targets similar to, for those of you that were around at our last call, talking about storage targets for coarse sediment, like active bars. So if we have some storage targets, then we can rearrange this equation here to look at, if we know what kind of output that we're getting out of the system, we can manage input as a way to try to balance a large wood budget to meet a storage target. But we kind of need to know how much the output is due to fluvial transport, decay, and chainsaws. So one of the things that Wes was doing as far as trying to get some ideas on future large wood targets, kind of the main report that he was drawing upon that was done by Cardno Intrix and CHM Hill in 2011 was compiling a lot of information on large wood storage density as a function of bankful width, largely from the Pacific Northwest. So Wes was placing these data points in here from Pacific Northwest, and then inventories that were done as part of the Cardno study were placed on here just to put current conditions, storage conditions into context, given the range of bankful width metrics that we have on the Trinity. And so it's showing that Pacific Northwest rivers have much higher large wood storage density than the Trinity. But there's kind of a major caveat too, that the climate in the Pacific Northwest is a lot different than the Trinity. And so, the document is trying to, I guess, come to terms with the differences in climate, the vegetation between these examples in the Pacific Northwest, given the more Mediterranean climate that we have on the Trinity, and trying to identify a potential zone that we can use for what's reasonable targets for large wood storage in the Trinity River. So this is kind of one of the bigger challenges that we're trying to kind of tease apart. There was also some work done by DWR to do some tagging on large wood. I don't really talk about that too much in here. I did want to show one little vignette of, I think, some work that Wes was doing, just tracking large wood transport during a 2017 flow. So we can kind of get an idea of how much output may be occurring just in the river. So what he did was during this large event, this is a release from Lewiston Dam. These flows here are measured at Douglas City, so we have some tributary creation. But he looked at this, he was tracking the number of pieces moving past an observation point at Douglas City in 2017 to get some idea of transport rates. And on the ascending limb on April 26th, where it was increasing from 8,200 to about 11,000 CFS, it's the first five bars on these histograms. So on the x-axis here, histograms of size class of log diameter in meters. So smaller logs here and then larger logs here. So this is 2 to 3 foot diameter here and then larger. And then the number of pieces per hour that he was counting. So on this ascending limb, he was getting, for these smaller size classes, 25 to up to 50 pieces per hour. And then for the next kind of size class that he was estimating, maybe more in the 17 to 35 pieces per hour. So smaller number of the larger logs, and then it looks like he's only got a couple that were even larger than that in the 2 to 3 foot diameter range. What I found was interesting is his second day of measurement, after several days or a couple of days of steady flows around 13,000, that the transport rates went way down despite it being a higher flow. So kind of similar to hysteresis that we see in sediment, there's probably a lot of large wood that's available for recruitment and transport on the ascending limb. And then as duration continues, the transport rates go down just because the supply has been already moved out of the system that's easily moved. So he started this process, but as far as I know, this is the only data that he collected. So skipping a little bit here, but kind of jumping ahead towards some of the initial ideas that he had put together, and we as a group talked about to some degree on draft vision and a strategy, is that we are trying to base it because on the Pacific Northwest conceptual model, because they've done so much work on this topic, but scale down for the Trinity River, given the different climate that we have here and the different vegetation types, because the Trinity is a lot different than the Pacific Northwest streams that a lot of this research has been done on. And that different reaches have different storage targets for large wood given their geomorphic setting. So confinement and slope and complexity of roughness elements that can trap large wood in the reaches may result in different storage targets for different reaches. And the other is that we encourage natural recruitment via large wood that's coming out of the tributaries so that it can come into the river and find places to deposit and store on the main stem. And that we're also getting recruitment from channel migration so that we're getting material recruited off the banks from floodplains and terraces, that we're encouraging both natural riparian regeneration and conifer regeneration on erodible surfaces so that in 10 to 20 to 50 years, we can get natural recruitment from future channel migration. And that another vision is that the storage is dynamic and that wood is routing through the system. So there's a mixture of residence time. So we're not building structures that are intended to stay there for 100 years, but that wood is actually moving through the system, and some of that wood may stay there for 10 or 20 years, and then other wood may be routing through the system on a much more frequent basis. And that those may be from individual wood pieces to accumulations of wood as large wood structures to more larger structures like ELJs that we've done in the past. And that this wood routes through the system over time, again, not fixed in place in time. And that we treat this large wood as a budget, similar to the coarse sediment, with periodic augmentation. So this augmentation, some of the ideas that we talked about is not only creating structures like the large wood structures or ELJs, but placing individual wood pieces that can move on a more frequent basis. And those can be done at individual rehabilitation sites, but potentially at other locations as well that aren't associated with individual rehab sites. And that this large wood would be done in coordination with other management actions. So flow management. So for example, one of the concepts that's discussed in the document is kind of like the high flow injection locations for gravel is actually putting wood in during high flows or potentially on the receding limb of high flows so that it can route down through the system and then deposit in the restoration reach. Another concept that's discussed is to combine it with coarse sediment management or use large wood to facilitate improvements in coarse sediment management via roughness elements. So either adding wood via placement or pulling trees over in less accessible reaches to create roughness that would assist in coarse sediment storage and retention in some of those more remote locations. And then obviously with channel rehabilitation projects. And those rehab projects, we'd be building features like expansion zones, mid-channel bars where large wood can accumulate and over time and grow and enhance their effect. Another strategy is to have diverse species composition. So not just conifers, but riparian and potential hardwoods, non-riparian hardwoods, with an eye to how those sources may change over time with climate change. So kind of looking into the long term for our future large wood supply. Having a large range of size classes. So most of our rehab projects are doing this now, where we're not just putting in large key pieces, but also putting in diversity of large wood down to splash size, such that we get more habitat benefits out of it and potential for biological productivity out of those finer materials. And as I mentioned earlier, looking at the different kinds of placement approaches that maximizes benefits but manages risks, not eliminates risks, but manages it so that we're have an eye towards not damaging infrastructure or property. The strategy also does not recommend non-natural hardware to retain the structures, but pinning, natural ballasting, those sorts of features. So if and when the channel moves or the structures or the wood moves, we don't have a lot of mechanical hardware out there. And that we promote natural regeneration on future erosive surfaces, as I mentioned before. And then of course, adaptive management as we go through this. So this process, or this large wood management strategy, is kind of eddied out with Wes's departure. I've been in conversation with Justin about trying to reboot this process. So I guess we're anticipating that NIMS will help kind of pick this back up, and we can get our core group back together. And that the next steps for this will likely first of all, get reacquainted with the existing draft document, and then start doing a more careful or a thorough review of the content itself. That would include the future vision, the core strategy, the draft storage targets that are in the document, and the corresponding management recommendations to meet those storage targets. And then we would need to develop a completion plan for the draft report to get it out of the eddy and towards a path towards completion, and then get it done. So that's all I had for kind of an overview. I wish I had, I guess, a final document to present to you, but I'm hoping that we can kind of pick this back up. The work that Wes had done here is we have a really good solid draft. There's some holes that still need to be filled and some comments, but I think that from a content perspective, we're probably 70+% of the way there. It's just kind of now filling in some holes and some gaps, stress testing it, making sure that we are comfortable with the recommendations in it, and then just finishing it up. So with that, I can take any questions, or we can move on, Chris.
Yeah, thanks a lot, Scott. That was really informative. We have actually a few minutes for questions. So if you can use your raise hand feature, which is in the reactions tab on the bottom, you can raise your hand and we'll try to get people in order. So James, I see your hand's up, so why don't you go first?
Yeah, thanks, Scott. I'm glad to get an update on this, and it just, I'm Wood to the Rivers always, really seemed like a great, I don't want to say no brainer. It's not a no brainer, but a great idea. Is the rest of this effort to complete this plan, is it funded, or would it require more support from the program to take it across the finish line?
We have a little bit of funding left to help, but I'm pretty sure that that NIMS has funding. I can't really speak to them, but I would assume that they do.
Okay, good. All right, great. Well, yeah, I'm looking forward to seeing it picked back up and completed. Thanks.
Me too.
All right, I see your hand up, Eric. Why don't you go ahead?
Okay, I'm not sure if this is a fully formed question, but Scott, you mentioned the contrast between the Trinity and the Pacific Northwest several times. And I would also say that there's quite a contrast to the rest of the Southwest. These, of course, exist on a gradient. And from my vegetation ecology experience, I would argue that we're closer to the Northwest than the Southwest. And I'm just wondering if this is discussed at all in the report, or what perspective you might take on that.
Yeah, it's definitely discussed, and we spent a lot of time on that when the group was meeting. So that trend or that gradient is certainly incorporated in here. The problem is, the geography that we're at in between Southwest and Northwest. They have less impacted rivers than we do in California, so we don't have a whole lot of quote unquote unimpaired rivers that are like the Trinity that we can use. So that's been a challenge I know that Wes had, is like there's a few examples, but not nearly as many as we have in the Northwest and perhaps in the Southwest too. But that's definitely a key part of the report. He spent quite a bit of time talking about that.
We've still got a few more minutes for questions. If anyone else has any, feel free to raise your hand.
Hi, this is Justin. I don't have a hand raising function that I can see. Can I put myself in the queue?
Yeah, go ahead, Justin.
Okay, yes, this is Justin Lee with NOAA Fisheries, and thank you, Scott, for the update. In terms of funding, we had a small amount in our interagency agreement with the program, and that was pretty much spent by Wes. And so I'd have to look at how much it was. I think it was only like 25. It was a really small amount. And anyway, what I wanted to say is, really the brainchild of this Larchwood effort, and when he moved on, and so we'll need to work, and we do plan on working with Scott and Justin. I'll pick this back up, but it's going to have to be a collaborative effort. That's all I wanted to add. Thank you.
Thanks, Justin. I'm glad that you're on the call, and hopefully I didn't mess anything up too bad, but we're gonna have to talk a little bit more and see how we can move this forward.
All right, we probably have time for one or two more questions if anyone else has any. If not, we can move on to John if no one else has any other questions. Thanks a lot, Scott, for presenting. I think this is your last one, so great job.
I think Eric has another question.
Oh, okay. Go ahead, Eric.
Yeah, this might be a little detail, but in your output, did you have decomposition covered?
Yeah. So there's decay rates in the Larchwood budget terms. So yeah, that was considered or is considered. That and chainsaws too.
All right. Well, thanks again, Scott, for presenting. Let's go ahead and move on to John, who's going to be presenting two of his syntheses reports. I guess whichever one you want to do first, John, is fine with us.
Okay, I'm gonna start with, I'll go ahead and start with the Cottonwood synthesis. Hi, everybody, I'm John Barry. Most of you probably already know me. How do I do the screen sharing piece?
It should be on the bottom and there should be a thing for share
Share
screen.
screen it, of course.
Yeah, and you are already co-host, so it should work right away.
So is everybody seeing my screen? It should be a title slide.
Yep, we've got it, John.
Okay. Well, so I'm going to talk a little bit about cottonwood seed dispersal today. I wanted to just acknowledge that this was a fairly multi-person effort. This would not have been possible without the diligent data collection of Jeannie McSoy from the Bureau in the Weaverville office. The synthesis really wouldn't exist without the data that she collected. So hats off and thank you to her. Let's see. So I just wanted to provide a little bit of background on the synthesis evaluation study. We were looking to try and get large trees and shrubs regenerated on floodplains up and away from the channel, and we were looking at trying to manage seedlings along the low water margin, which I'll talk about in the next talk. But cottonwood recruitment has been focused on because they are the largest trees in the riparian corridor. They grow very fast, and they are heavily reliant on the snowmelt hydrograph, which was something that we were trying to get some forms restored in the flow evaluation study. And so initially we had some qualitative observations that were made in the late 90s and early 2000s. And we used those initial observations to guide our seed dispersal periods. And we, as the work evolved, folks in other regions were beginning to find that seed dispersal for cottonwoods was variable, dependent on temperature and a few other variables. So the punchline from this is it's really expensive to spend your water and miss your target. So if you have a stream flow that you're trying to release into the system for the purposes of regenerating cottonwoods, missing the seed dispersal period doesn't give you the desired result that you're looking for. So what we wanted to do is we wanted to utilize the data that had been collected and use that in some way to define a target seed dispersal period that could be consistently applied, if possible, when we were doing stream flow scheduling or planning each year. And so one of the things we wanted to look at is, you know, how does this seed dispersal differ between trees, years, and site? Is there an upstream to downstream effect? How variable is it? And we wanted to look at the variability of the timing between trees and between sites and years, and look at some of the pieces of, is it more date dependent, or does biological heat accumulation actually have a role to play in the timing of seed dispersal? So I'm just going to quickly go through the sites. We had 4. Little fun fact here is that there are male and female cottonwoods, and cottonwoods disperse seeds over a very discrete period of time during the year, and cottonwood seeds are generally viable for about 7 to 14 days after they're dispersed by the tree. So there's a very short window of time where seeds can be dispersed, land on a surface, and begin to grow. So we selected sites from upstream to downstream. 4 trees, the green dots are all trees that we've been studying. However, the circled trees in this slide are the ones we used in the study. They were the female trees. Loudon Ranch, we had 4 trees. Indian Creek, we had 3 females. Douglas City, also known as our Weaver Creek site, there were 6 trees. Lower Junction City at the lower end of the river, there were 11 trees. And the 5 circled trees here had been previously studied in 2004. Now, when we started this whole adventure, we kind of thought that this was going to be a very straightforward ANOVA analysis, and that we expected there to be a high amount of variation between dispersal timing, but that there wouldn't be much difference between sites, and that we would find that they were fairly consistent between years. Now, our thought was that if the seed dispersal period varied interannually, then there were other things that were affecting the seed dispersal period. If it was consistent annually, then something like photo period and date, which are correlated, would be a good descriptor. So this is where we started out at the beginning of the study. And we rapidly started looking at the data in a bunch of different ways. But really, let me tell you a little bit about the data itself. The trees would be visited, a consistent observation point was used, and the percent seed dispersal was estimated for the whole tree. And there was a couple of trees that had some problems, whether they were eaten by beaver or they turned out to actually be a male. But that, you know, we kind of went through and scrubbed the data and looked at that. We did test for normalcy and distribution, or for normalcy. And what we found is the data was not normal. We also couldn't transform the data because many of the 0 or no seeds dispersing were real data points. And at some point in there, we began considering that rather than using the percent of tree dispersing seeds, that it would be better to just use a binomial data where if you were dispersing seeds, you got a 1. If you weren't dispersing seeds, you got a 0. So we had some data to work with, and we converted the data into a couple of different things. We kept the original seed dispersal data, and we mined out the median seed dispersal date, and I'll talk a little bit more about that. As well as the peak seed dispersal period, and then finally the binary seed dispersal that we were looking at, where it was just seeding yes or no. We applied different statistical approaches to each of the data to evaluate whether or not there were indeed significant differences between site, year, tree. And then we explored a little bit further as to whether or not we could actually develop some form of predictive model for the onset of seed dispersal. Now, this is just an example of a line plot of the raw data for all the years that we collected the data. There's a fair amount of variability here between years, which is something you would expect. But between May 8th and May 29th, 100% of the seeds, or 100% of the trees we were looking at were dispersing some amount of seed. Some were low, some were high, but regardless, in all years between May 8th and the 29th, 100% of seeds are being dispersed. Now, I could dust myself off and say, okay, we're done. Our seed dispersal period is May 8th to the 29th. But as folks who are familiar with the stream flow management process are aware, usually we are going from peak to recession during this time period, and we would like a little more discrete target for when we're likely to achieve the most amount of seed dispersal relative to our flow action. So because we have non-normal data, our initial analyses were non-parametric, and we applied a Kruskal-Wallis rank sum test, and we utilized the binomial data initially. And this was just to look at whether seed dispersal was different among years, sites, and trees. The second analysis that we did initially was just to develop box plots in the standard form. And we looked at the Julian date of peak dispersal, and we looked at when the beginning of peak dispersal occurred. And I'll talk a little bit more about that. So just looking at the Kruskal-Wallis test results, our hypothesis here was that there wasn't going to be any difference between trees, sites, or years. However, what we found was that there was indeed a significant difference between years. However, trees and sites were not significantly different. This is good news because this means that trees up by Lewiston are no different in terms of their seed dispersal period and variability than the trees in the lower river. So if we were targeting the whole river to have our effect, which we are often trying to do with the stream flow management, then it's good we can treat it as a whole population as opposed to different populations with different seed dispersal periods. So that was really good. The weird one for us was it was different between years. Now, this implies that there could be, in fact, some relationship to weather, heat accumulation, or some other variable than simply date or photo period. So we went and did a post hoc analysis with the Kruskal-Wallis, and we wanted to look specifically at what years were different. And this didn't help us a whole lot. In the sense of 2015 and 2016 were not different. However, 2015 was a dry year and 2016 was a wet year. So that was a little odd. And, so we saw these differences in water years, but we didn't really have a plausible explanation. And for those of you that have been following this saga for a number of years, one of the stories I usually like to tell is that in extremely wetter years, when it's colder longer, we'd have later seed dispersal. And in drier years, when it's warmer earlier, we would have earlier seed dispersal. However, the results didn't really suggest that that story was even vaguely true. So then we wanted to look at the onset of peak dispersal. In other words, when are the most seeds being dispersed by the tree, by each tree? Now, my sum total of trees was 39. However, we had to drop one out because one was a male. The important thing to take home from this message or from this slide is that there's a lot of variability in the onset of peak seed dispersal, and that variability occurs over a 40-day period. So this isn't overly helpful in terms of defining a target period, because the seed dispersal onset for trees is highly variable between trees and sites. Now, looking at this a little bit further, the definition for peak seed dispersal is the first day where more than 75% of the tree canopy is dispersing seeds. Each of the blue dots in these box plots are trees. And so the box plot on the left is looking at year, and the box plots on the right are looking at site. The thing to keep in mind here is that this is a little bit different of an answer than we got from the Kruskal-Wallis test, but the Kruskal-Wallis test was looking at binary data. This is actually looking at the peak dispersal as a percentage of the tree canopy and when that occurred. So basically what this suggests is that there are differences between years, but there aren't much difference between sites. So we took this, as you might expect, quite a bit further to kind of get a better idea of how much variability there was within each site. And you can see for each site, the amount of trees that are in peak dispersal is highly variable between each year and between each site. So there's a wide amount of variation occurring in any given location that we were monitoring in any given year. So we wanted to take this, of course, a bit further because we still haven't really landed on anything better than our initial analyses had looked at in terms of seed dispersal period. Remember that May 9th to May 28th or 29th period. So we haven't really narrowed it down yet. So we started looking at this idea of median seed dispersal, and then relating median seed dispersal to the biologic heat accumulation or degree hours that each plant is receiving, and then trying to develop some form of model for us to make a predictive, to make some form of prediction for when seed dispersal would begin. So just looking at the raw data, the upper left graph is just the percentage of seeds that are the percentage of seed dispersal for all the trees combined as it relates to the accumulated heat or degree hour. Now, in order to calculate degree hour, we use an integrated pest management tool that's available at the UC Davis website. This is something where you can basically use a long-term weather station and calculate the amount of degree hours that are being accumulated across a fixed period of time that's defined by the user. And so I used, I think it is the 5-cent weather station to basically develop the degree hour accumulation. And that is the closest or one of the closest weather stations, I believe, to Lewiston. No, I didn't use 5-cent. I actually used the Lewiston weather gauge. Anyway, it was elevationally and location appropriate for the upper end of the river. We used one model for all the sites. And so the shortcoming of that data is that it doesn't get at the actual environment that each tree is receiving. It's just getting at a generalized heat accumulation for the river. And what you can see in the raw data, as well as in the data that we were working with in R, is that, yeah, there's a pretty good box between 1900 and 2900 hours of heat accumulation where seed dispersal occurs, but it's variable between years. So this isn't overly helpful in narrowing down our seed dispersal target window. However, it is suggestive that there is, at least at a qualitative level, a relationship between degree hours and seed dispersal. So this is sort of the same story here. We also looked at it by site because we just, again, looking at how the sites were different as well as the same. And one of the things that you see here is that some sites tended to go a little bit earlier and some sites tended to go a little bit later. And this is probably because of site level differences in the way heat is being accumulated, not necessarily large differences between these populations. So this was just kind of our initial scratch on the surface of degree hours with site and seed dispersal. So we started to look at this thing called the median percent dispersal. And bear with me, I'm going to ask you to wrap your brain around this a little bit, because what this is that for each week when the data is collected, the median percent seed dispersal is the data point that was used from all 38 trees. One way to look at this is that when the values are 0, some trees are not dispersing seeds. But when you have values that are greater than 0, all trees are dispersing seeds. Now, you can see on the graph on the left that there's a fair amount of variability with 2017 and 18 largely following the same pattern, but not the same magnitude. But then 2018 is way off there to the right, where it is quite a bit hotter to get the onset of seed dispersal. The raw data for seed dispersal is shown to the right. So this median seed dispersal is actually teasing apart differences in the data that would not otherwise be discernible. But what we found was that when we looked at the highest median value and we just plotted that across the weeks, that basically week 10 and week 11 are the weeks when the highest amounts of median seed dispersal are occurring. In other words, this is when the most trees are dispersing the most seeds in the river corridor from Lewiston to Lower Junction City. This was a really important result for us because that suggests that we could actually target the 15th through the 31st of May regularly, and we would have a very high chance of each site getting some form of seed dispersal, assuming that there were females nearby. And so this is like, yay, punchline. And this is a very strong relationship. So now that we've got our seed dispersal period narrowed down, we want to look a little bit more at the environmental data that is, or the environmental conditions that are driving some of this. And again, I'm coming back to this idea that Julian date and biological heat accumulation are two variables that are leading us down the path of a more refined seed dispersal period. And so the relationship of seed dispersal and Julian date is here on the left, and then the accumulated hours of heat is on the right. Doesn't come overwhelmingly with a relationship to me, a lot of variability there. So what we did is we started to create different linear models and looked at what kinds of, what our best fit was. And so the simplest models were that the trees were what was driving it, and it gradually got more complex until the lower models, Model 4 and Model 5, we were looking at the percentage of trees dispersing seeds, or the yes or no component of dispersing seeds as it related to Julian date and accumulated hours. These had really good fit relative to just site alone, years alone, or trees alone. So this suggested that we were on the right track, that accumulated hours and Julian date did indeed have some interactive effect. But the real question was, could we do better than just week 10 and 11? So what we did is we used the general linear model 5, and we looked at 5 different scenarios for accumulated heat, and we plotted out the results to see basically how the probabilities might change between the different heat scenarios. And what we found is that all these lines basically intersect at Julian date 139, May 19th. Okay, so that's 4 days after our peak dispersal period that we defined in a far more simple way occurred. So this was all good news because this fit within our target window. And we had a high probability of that occurring on May 19th. There's a lot more to this analysis. I suggest you have a look at the synthesis report itself. However, it was great to see that these results not only supported each other, but also showed the influence of how degree day or degree hour was influencing the peak seed dispersal period. So just to give you an idea of how that worked out, here we are with our raw data with all of the seed dispersals, and with the black line, and just shows where the model would predict the onset of the peak dispersal period, or for all trees, and that would be May 19th. So a little too specific to make a target, but it definitely corroborates this idea that May 15th to May 31st. So the conclusions that we made broadly were that we don't have differences between, is that given the variability for each tree in site, there's not a huge difference, or there's no significant difference between trees in site. There is, however, a lot of variability year to year. However, when we look at the median peak seed dispersal, it occurs in all the years that we studied, which were 5, in weeks 10 and 11. That to me, that one result really kind of blew my mind. That was really good news for me. And then finally, as we explored the relationship between the timing and biological heat accumulation, there was clearly an interaction between the two. And it may be more academic to want to understand that interaction between the heat accumulation versus timing. But it was pretty clear that there was an interaction there that was significant and could ultimately be used to develop some kind of predictive model for the onset of seed dispersal. So the heat accumulation is not the only, biological heat accumulation for development is not the only variable that could be affecting seed dispersal. And so the next steps could include looking at the relationship of seed dispersal to other environmental factors. It would be interesting, potentially important, to conduct a cluster analysis using tree-specific environmental variables. In other words, put hobo sensors and light sensors out at the sites to get site-specific data, as opposed to using a regional weather station. And then finally, the holy grail here would be to develop a gaming tool that uses the results from the general linear model to kind of look at how timing could be better or more specifically designed year to year to meet target seed dispersal. So that concludes this synthesis report presentation. I'd like to open the floor up to questions as folks have them.
Thanks a lot, John. Kyle, I see your hand is up. Why don't you go ahead first?
Thanks, John. Really interesting. I like how targeted we're getting with when we can recruit cottonwoods across years and space. One thing I couldn't help but think about is what we've learned about frog recruitment, and how, while the timing of recruitment can be, or spawning or egg mass placement can be spread across a large time frame related to temperature, the most successful are those that occur early. And I wondered if you had any data or experience that would lead you to any interpretation of the relative success of cohorts when seed dispersal occurs early versus late.
Well, we don't have very many structured experiments that would separate early, middle, or late seed dispersal as it relates to cohort placement. The initial point here was we were missing seed dispersal, or we weren't hitting seed dispersal very well with our stream flow management. And so trying to get just narrow down a period that would give us better results, more seedlings than zero. And I think that this gets us there. The question of separating out plant success relative to early seeding and late seeding would be a fairly complicated and expensive study. And I think right now, if we were getting some results that were higher than past results, just in terms of just getting the seedlings on the ground, that would be a real win for us. How they then performed, it's a little different than a frog that has a 1 year life cycle to metamorph to adulthood. Many biological competition issues come into play as the plants get older, in terms of herbivory and interspecific plant competition. So it would be a fairly complicated study to get to a mature tree and whether that tree came from early seeding or late seeding. So kind of a long-winded explanation there, but it's an interesting thought.
Yeah, thanks. And I realize this is a huge advancement in our ability to meet the needs of this species in early development. And that's awesome. I guess I'd be interested in what would be needed to look closer at that. I guess you'd need to know seed dispersal windows over a longer period of time.
Well, it sort of touches on something that Bill Brock had brought up after I presented the synthesis originally, which is he's been watching the cottonwoods out back at his house in the Sacramento for a number of years, and meaning more than 4 or 5. And what he's noticed is that the seed dispersal period is becoming earlier and early every year, which is something that with climate change, we're beginning to see more and more of for other species, which is a process called vernalization. And without collecting long-term data, it would be very hard for us to know whether the seed dispersal period was actually changing or whether it was within the variability of the population alone. But it'd be something that, we should certainly talk about more. And at what age would you say that timing what part of the seed dispersal period led to better recruitment? That would all have to get kind of worked out.
Thanks, John. Our next question is from James. Go ahead.
Oh, yeah. Hey, thanks, John. Great presentation. I really enjoyed it. And I don't have a lot of specific questions because I was so familiar with it while it was happening. But, I just wanted to point out that there's a lot of different reasons why we maintain black cottonwoods as a focal organism of the program, focal species, why we want more of them, a whole list of reasons. But, you kind of think, well, the tens of millions that a cottonwood produces and the extent of their seed dispersal period, we ought to, that ought to mean something. But in reality, in certain areas of the Trinity, there's a real shortage of female black cottonwoods, which makes the ones that are producing seeds all the more important. And that's why, one of the reasons why this study came about, because we want to make the most use of the seed-bearing cottonwoods that we have out there. And, you know, I was just thinking that while you were presenting, and I wondered if you had any thoughts on that. It's this kind of a conservation, a way to conserve, wisely use the trees that we have by synchronizing our releases with their seed dispersal period as tightly as we can.
Yeah, it's a great point, James, and you make an excellent point that we are seed limited on the Trinity. We don't have, there are large populations of cottonwoods in some locations and other portions of the river where there are one or two. Yeah. And maybe there will be a point where we have thousands of them, and this is less of an issue because we're being overwhelmed with seed, and that would be a wonderful place to be, I think. It is using the best of our resource or targeting it to meet the greatest amount of available seed that cottonwoods are producing. But the other component of it, the Trinity is not unique in trying to recruit cottonwoods. And in fact, considerable amount of work, water, and brain power has been put into trying to get cottonwoods on the landscape. And water is probably our most expensive resource that we put out there from the restoration standpoint in terms of the value of the water in gallons. And we have so many different competing interests with how we want to use the water relative to our annual hydrographs. So between the seed dispersal and wanting to use our water effectively, those two kind of marry to lead us down the path of getting the most bang out of the flows that we have that are targeted for cottonwoods, while the cottonwoods are able to disperse seeds, or while they are dispersing seeds. So it's a great point.
Thanks. Yeah, thanks for the presentation. It's really interesting.
You bet. Anybody else?
Not seeing anyone else, John, so guess you can go ahead on to your next one.
Okay, let's see if I can do this without putting anybody's eyes out. All right. Ta-da! All right, so back to the slide. Everybody see the title slide okay?
If we got it, John.
All right. So I thought I would go to the riparian encroachments of this last, because this is probably, well, I've been working on the encroachment component of this since the flow study in the 90s. And this is the process of riparian encroachment is one that has been debated and thought about a lot for the Trinity program. And certainly the Trinity is not unique in riparian encroachment, but oftentimes we think of it specifically in terms of our river, the Trinity. And we initially, in the flow study, as well as in the years following, we thought about encroachment before the dam, where there was a lot of fish habitat. Certainly there was some vegetation encroachment, and there was some level of riparian berm. And just so that I can define my terms for everybody, let's see if I can actually get a pointer here. So this cross section, the black line, or actually, yeah, the black line is the pre-dam cross section with some riparian vegetation up and away from the channel. And then the idea is that plants encroached and we had this change in channel shape, this narrowing, deepening of the channel, and that this had some effect on salmon habitat or rearing habitat specifically. And so after the dams closed and regulation began through the 80s, we had a significant encroachment issue where willows largely had been growing along the low water channel. We had a big reduction in habitat from flow, as well as change in channel morphology. And we had this, we had more representation of a sediment berm. After 14 years of restoration, encroachment is still a big issue for us. The berm is a lot less of an issue, and habitat is certainly more than it was in the 80s. I wanted to just start with kind of what my conceptual plant life history model was and how it related to how it relates to the different plants that are out there. You have a fall seeding group that's white alder, and some other species, Oregon ash, and their strategy is to put seeds out onto the landscape as the winter progresses, and their seeds are longer lived, 1 to 2 years, and they're delivered in sediment. Arroyo willow, cottonwood, tree willows, narrowleaf willow, they all have kind of the same seed story where their catkins are producing seeds, their seeds are viable for a short period of time, and the environmental conditions during their seed dispersal and following largely have a big role in how they get out onto the landscape. This could be, generalized in terms of a flow chart, and where the first year is really about getting out on the ground, getting your roots to grow to permanent soil moisture, and then getting as big as you can that first year before you go dormant. It turns out that historically, we used to have very large winter flood peaks and large spring peaks, and that these peaks were responsible for scouring the channel bed and many of the physical changes that we saw in the river. And at that point, many of the plants would be killed. They wouldn't make it into growth. However, if they could get through growth the second year after seeding, largely they were able to establish. It's a little more complicated than that, but the idea was that after the first year, when they were young and small, the seedlings were the most vulnerable to scour. So the idea was then that there was a window of opportunity for each species, for cottonwoods, willows, where if they, sometimes you'll hear me talk about this as the Goldilocks location on the cross section. If they're too low on the cross section, they'd get scoured away. If they're too high on the cross section, they would get desiccated. And that, the place between desiccation and scour is largely where we would see riparian establishment. Now, in a river that's moving, or migrating or changing, these areas of establishment are often left behind or isolated, and new areas of establishment are created. And that's largely responsible to all of this variability within the hydrograph. And it's worth noting that before dam closure, the Trinity was quite variable. Just whether you look at it as a line graph or a raster hydrograph, you can see that just by the amount of colors in the raster graph, you had areas of high flow for most of the year and low flow later in the year. In the dam, it's all low flow. During the maintenance flow study, it's modest flow. And only after the record of decision came into being do you begin to see more of the area with higher flows. Well, that flow variability really plays itself out depending on where you are in the hydrograph. So this chart down here is just what it looks like coming out of June into September before impairment. A lot of variability between years. The red lines are dry years, the blue lines are extremely wet years, but you're looking at a large amount of flow changes between the different water year classes. This graph is showing you what the difference is after the dam was completed. And so we took all of this variability and effectively forced it into a very small flow window. Now, another way we can look at summer base flows is that as the dam was completed, we had near constant 150 flows, 150 CFS flows as our lowest flows. Then after the Andrus decision, they went up. And then later we found that from a temperature maintenance standpoint, that they needed to go up again to keep the water cool down in Wetchupec. So we saw this gradual increase in summer base flows as we went through time, but they still were largely, there was a floor. And this graph captures that floor really, really well. So the idea here was that before the dam came in, that you had basically different places on the cross section where the window of opportunity where you could get plants started, and that it was the annual scour that basically kept the lower end of riparian establishment from coming down into the low water channel. Well, after the dam was completed, those dynamics changed because we lost our peak flows and we had a very steady, even flows for a very long time. And so you had the older riparian vegetation that had established pre-dam up and away from the channel. But very quickly, you had riparian vegetation, I think Ritter saw in 1968 at Indian Creek and Rush Creek, that the plants were growing along had established along the low water edge. That's basically 4 years after dam completion. We were already seeing this process occurring. Well, as the plants grew, so did the sediment that got trapped inside of them. And that sediment formed a berm or something that could confine the channel. And we went from a wider channel with greater flow resilience across many, stage resilience is really what it is. A lot of area inundated by different stages to a very narrow area that didn't really, you got deeper, but you didn't get much more change than that. Well, the effect of this is that when we looked at the tractive forces on the bed, most of the tractive forces of the shear stress was caught between the riparian, the edge of riparian on both banks, and the force itself was pretty evenly distributed or peaking in the middle of the channel. So this is a little bit problematic because if you want to scour your margins, the relationship of how your shear stress is distributed isn't at the margins, it's focusing on the center of the bed. So you'd kind of neutered the ability of the river to do the work on the margins that you wanted it to. So one of the things that happened was in 1993, some folks scraped off riparian vegetation at about 400 feet of channel in 9 locations, from the dam all the way down to Pear Tree Gulch. And this idea was that, you know, we're going to make the channel wider, and we're going to have one bank where river flows would have access to a wide range of surface area relative to the water surface elevation change. 2 years after those sites were constructed, in water year 1995, we began to have a series of wet years. And those wet years were very large, with peaks in 1998 reaching larger than 14,000 at the downstream end, and certainly above 6,000 at the upper end. What was important about this was that at the feather edge sites, or the bank rehabilitation sites that were constructed, bars formed. And you might remember the way that distribution looked at the unrehabilitated cross section. It was fairly uniform, or it was just simply a U. What we found when we measured the shear stress at the bank rehab sites was that in lower flows, the tractive forest peaked in the Thalwag, but then as flows began to increase, the peak moved, adjusted, and went up and over the bar to where it was finally focused at higher discharges up here on the bar. So we had a greater range of shear stress effects in the rehabilitated channel than we did in the unrehabilitated channel. This was really good news, because this indicated that a mechanism that we could use to maintain these sites was potentially high flows, assuming, of course, that they did the job that they needed to do with scouring plants. And scouring plants was just one objective. Bedload transport and surface mobility was another. So in 1995 through 1997, I did a lot of hands and knees sorts of studies, and I looked specifically at the relationship of where seedlings initiated, and then finally with repeat surveys where they might establish. And even in the 1995 to 1997 period, while we had a lot of changes physically, we still had a group of seedlings that established at the far edge of the channel. And so the bar itself, we'd see seedlings come, and then in subsequent flows, we would see them go. But there was a limit at which we could not scour the plants. Now, one of the things that I did during this period was to pull up a lot of plants and measure seedling root depths. And this was done, well, there's about 800 plants that were dug up across several cohort years, up to about year 5, when the plants were so big I couldn't really dig them out of the ground anymore. But treating the roots like a cumulative distribution, like a pebble count, where they are the percent of roots that are smaller than, we reach 100% of the roots are smaller than 140 millimeters for a young of year plant. For a 1-year-old plant, 90% are smaller than 240 millimeters. But this idea was then related to some of the surface, the gravel work that was being done at that time period, to get a sense of, if we were able to move a certain size gravel, would the mobility of that gravel also equate to killing of a certain amount of plants or cohorts? And we loosely developed a relationship where for young of year and for 1-year-old seedlings, if you were to mobilize the surface layer of the channel bed, you would kill roughly 60% of 1-year-old plants and nearly 100% of young of year plants. So if we follow those same cross sections through time, after the 1998 wet period, we entered into what I'll refer to as institutional drought period. The flow study was being wrapped up and the releases into the main stem were modest. And during this time period, just following the 1995 cohort, we began to see topographically sediment being retained on the bank and the berm reforming. And so the question started to become, what are the flow recommendations that would be necessary to manage not only the berm, but also the young seedlings? So in the synthesis report, I broke this up into a series of time periods that were related to the flow evaluation study, the early record of decision study, and then other periods as we went along where either the sampling or the method of management changed. And so from 1993 to 2004, what we found was that there were cohorts that came out and that there were cohorts that were scoured. And as we go through this, and the idea is that the cohorts that were scoured were related to the peak discharges, and that the mechanism by which these plants were dying was largely mobilizing the channel bed. So during this time period, the 1993, 1998, and the 2000 cohorts were not managed using flow very well. And we were able to show that these cohorts had survived through 2004. However, most of the cohorts, or roughly 7 of them, had been removed as part of peak flows. So I'm not going to go through and read all of this because this is a summary really of what I've just covered. However, this period of study is what started putting riparian scour objectives together with the peak flows that were included in the flow evaluation study. And what we found was that when bar surfaces were mobilized, a majority of the 1-year and younger plants were scoured, and that as plants got older, up to about 3 years, there was a limit on being able to scour the plants away with larger flows. And the idea that we landed on here was that we could feasibly manage 1-, 2-, and 3-year-old plants with flood peaks, but that after 3 years, we entered into a window where we were no longer able to scour the bed to a depth where we could kill the plants. And so this became the foundation of the work as we went into the record of decision, where our flows were essentially codified. Now, in the flow evaluation study, each piece of the hydrograph had to be justified in the sense of there were specific objectives, thresholds reached, and then an expected outcome. And this set of flows was supposed to interact with our cross sections in a way where along the lower edge, we would expect scour, but on the developing floodplains and upper bars, we would try to promote our woody plant establishment. Now, the encroachment synthesis doesn't focus at all on the upper bar establishment component. It just looks at how effectively we have been at managing the edges of bars and the edges of the channel, since immobilizing them tended to lead us down this path of a more narrowed channel that was deeper. So shortly after the record of decision was signed, there was a lot of discussion about what the role of encroachment would be as we moved forward in the program. And one of the ideas that was presented there was that flows that were included in the record of decision, along with coarse gravel augmentation or coarse sediment augmentation and channel rehabilitation, was sufficient to manage encroachment. And the converse to that was that after a period of dry years, we would have plants that were too large to be scoured, and that one of our problems was this period of 3 years or more of no flood peaks. We would go down the path of the river being encroached and getting narrower, and the physical changes we didn't like. One of the big pieces here is that we were expecting that with coarse sediment augmentation, that we'd actually be able to make the channel bed finer. And by finding up the channel bed, lower flows would mobilize it. And so lower threshold flows would be able to scour away the plants. So that's one big part of coarse sediment augmentation, having an influence where we lower the flows that are necessary to mobilize the bed. The other component is how often in our 108-year period of record do we actually get dry years that exceed 3 dry years in a row? So this chart up here is just looking at that specific question. So we have a lot of places, a lot of time where it's just one water year, one dry year, or one wet year in a row. We have 3 or 4 instances where it's 2 in a row, about the same for 3 in a row. But this is not nearly as frequent as we thought within the 100-year period of record. Now, I can't forecast whether this would change as part of climate change, but certainly using the period of record that we have, it's highly suggestive that 3 or more dry years in a row are not a super common occurrence on the Trinity, at least historically. And the most notable period of 9 dry years in a row occurred during the Dust Bowl. So armed with these hypotheses of more water, gravel augmentation, this is all going to lead to unicorns and rainbows. It's going to be great. We've started going out and just monitoring monitoring the river. Generally, we focused on channel rehabilitation projects for the 2005 to 2009 period, because these were locations where we had manipulated the physical channel bank to basically get a different effect. And since these were places that the program was investing in, these were locations where probably our encroachment dynamics needed to be managed successfully, because encroachment happens to be occurring in one of the same locations as fish rearing. And if encroachment occurs, then we get this disconnection. So remember that out there on the landscape, from 1993 to 2002, we were able to get 4 cohorts out there. But then as we started implementing the record of decision flows in 2005, we started to see that we were managing, we had seedlings get out, we had seedlings survive, we had them then die. And so at the end of the 2005 to 2009 period, there was only one cohort during that time that survived. Now, is the world spinning off into the sun because of 4 surviving cohorts? Probably not. But the idea is that we're gradually stacking this area, or basically we're increasing the inventory of plants in locations where we don't want them. But to only have one cohort surviving, it has more to do with this period of, we had a very wet year in 2006, then we had a dry year in 2007, and a normal year in 2008. And so we have 2 years of plants being established. By the time we get into 2009, where we have a dry year again, there's an insufficient peak to be able to remove the 2006 cohort, and the 2006 cohort survives. And this is all based on data that we were collecting during this time at cross sections at channel rehabilitation sites. Now, in 2010 to 2012, we started wanting to look at, we started looking at the relationship between size and year class, because one of the things that we found was that there was a lot of variability in size to age. So we did some work here in order to be able to develop, we could use size class because it could be measured as opposed to cohort, which had to be the other thing that happened during this time period was we moved to a different thing at channel rehabilitation sites previously. Okay, so at this time, we also started trying to get at the level of risk of encroachment. So if you were a 1-year-old seedling and you had only been out there for a year and there'd been a flood peak, you were a very low risk of encroachment. If you had a lot of 3-year-old plants out on the landscape, you had a very high probability of getting past your management window and encroaching the channel. So one of the things that, sort of continuing this theme of who lives and who dies, during the 2012 to 2013 period, we found that, well, I should mention that we were also allowed to get to 11,000 CFS for the first time during this time period. So we, at the dam, all of our obstacles were cleared and we could achieve our extremely wet year peak release. And so we did so. At the end of this time period, we still only have the 5 cohorts, the ones that were pre, and the 2006 that was after the program had really gotten moving. So this kind of tees up the next. So far, we've been managing to keep the seedlings at bay from the 2005 to 2012 period. But in 2012, we had a normal year, and then we entered into a 3-year dry period. So this is the time for us to actually dig in and look at what our whether our hypothesis around seedlings greater than 3 years old actually move into an encroachment scenario. And so this was this was a very challenging time for a lot of reasons. And one of the things that we had been having trouble with was that the Gertz 400-meter segment that we had been using as a sampling frame wasn't a great sampling frame for us to be looking at encroachment, because largely what we were concerned about is plants immobilizing our gravel deposits or gravel bars, and low features that were also providing rearing habitat. And so we moved to just focusing on low channel features or gravel bars in the river to look at were seedlings surviving past the encroachment threshold. And so we would float the river. We identified we would map all the gravel bars with a point, give them some attributes, and then we would subsample using the general randomized tessellation routine to give us our samples that was spatially balanced throughout the river. And so one of the things that we just kind of can look at here is that in 2012, we had 69 points that fit this, but then for the next 3 years, we had over 100. Now, whether this is super important is really looking at the complete sample of bars, which largely remained unchanged from 2013 to 2016. Now, sampling through this again, we see that we get into this period of dry years with the exception of 2015 and 2016. And even though 2015 is a dry year and 2016 is a wet year, we have the 13 and 14, which were dry years. So if we just do the math where I have a seedling in 2012 that survives, this flow threshold is too low to remove that cohort, so it survives to the next year. Now it's 2 years old. This flow threshold is too low to remove that group of seedlings, and it's also too low to remove the previous year's seedlings. Finally, in 2015, even though it's a dry year, the stream flow management group said our risk was too great for letting these seedlings survive. And through a lot of discussions, we landed on a Lewiston peak of 8,500. Well, 8,500, based on what we thought we knew at that time, was inadequate to kill 3-year-old seedlings, but it was completely capable of killing 2 and 1-year-old seedlings. So we went ahead and said, well, we'll manage the 1 and 2-year-old seedlings, and we'll just forego the risk for 3-year-old seedlings because it's just too much water in a dry year to leave to a peak without focusing on other system needs such as water temperature and fish health. So in theory, this should be the end of the story. We should have 2012. It should survive forever based on what we think we know, and it's past the 3-year window. But interestingly, in 2016, when we had a wet year, we could release a little bit larger of a peak. And it turns out that the combination of a wet year release followed by a wet year release was actually capable of eliminating the 2012 cohort. Call it that was something that was not considered during the flow study. Previous sampling hadn't suggested that this would be effective. However, here we were with 1 year, which was too low to kill the 3-year-olds, but the next year was capable of wiping that cohort out. This is something for us to definitely be considering in dry periods as a way of managing our seedlings. We don't have any monitoring in place anymore to look at this. However, that's something that we could focus on as a way of managing plants in dry periods, and we could develop a monitoring plan to actually look at whether the 1-2 punch was an effective way of managing plants. So a lot of things over the years that came through all of this. And there are a lot of different views and opinions about the role of plants in the river. However, something to just kind of think about is that in a sediment, there's one level of bank cohesion. As plants begin to establish along the channel margins, that cohesion begins to increase. As the bank cohesion increases, the propensity of the channel to be a single thread channel also increases. So depending on what channel type is possible in the Trinity, plants are a big role in whether it will be able to move, whether it will be single threaded, and whether it will maintain itself. Something else to think about here is the flow evaluation study visualized the peaks as occurring within the water year types that they were assigned. In other words, that a 6,000 CFS peak would occur in normal years all the time, and that extremely wet year releases would only occur in extremely wet years. Now, the record of decision gave us some flexibility with how we manage our peaks, and the streamflow work group has taken that flexibility to heart. And so the years that are circles here are years where we had a water year class of dry or wet, but our peaks are much larger than what would have normally been assigned during those years. And so effectively, we've changed the flood frequency curve to have higher peaks more frequently. And this was done for a number of reasons, the least of which was to juice up the river to try and get some geomorphic change happening. And of course, that strategy was largely effective at managing seedlings during that time period. So the increase in peak frequency and magnitude and frequency was a really good thing. And the fact that the streamflow management work group has that flexibility gives it a certain ability to manage encroachment in a way that wasn't necessarily originally anticipated, though adaptively managed. The other thing is that, you know, channel rehabilitation design has needed to consider and does consider encroachment at all kinds of levels. But the thing that's important about this is we never intended for vegetation to be a yes or no thing, where we don't want it next to the channel, or we do want it next to the channel, or we don't want veg kind of thing. And so that isn't true. Vegetation structure and patterns adjacent to the channel are an important component of both terrestrial habitat, but also aquatic habitat as those surfaces get inundated. Our strategy to lower surfaces across the board, that's a great one. We're more likely to get more of the plants that we want, like cottonwoods. However, at the same time, there are trade-offs there that each of the design teams needs to consider. The other thing is that encroachment is not synonymous with the berm. You can have encroachment without a sediment berm. And this is something that is largely lost, because when we talk about riparian encroachment on the Trinity, we seem to think about berms only. You can encroach the channel without having a sediment berm. So managing sediment berms is just a component of fine sediment management. It's not necessarily it's not necessarily limiting encroachment from happening.
Well, and so many of their photo points are.
So the other piece here is something that I alluded to at the beginning, which is our coarse sediment augmentation was supposed to reduce the sediment size and make it easier to mobilize the channel bed with lower peaks. And that is something that did not happen. Sediment sampling has shown that we're not seeing any real decrease in particle sizes. It's largely localized around our core sediment augmentation locations, not riverwide. So there's a lot of mechanisms that could be used to cause mortality in young seedlings that were not considered. Large wood was a missing component from the record of decision in the flow study. Certainly, as more and more large wood is added to the channel and our riparian structure grows to increase the input of large wood, that's something that could certainly affect channel formation and morphology and change the way shear stress is distributed along a cross section. Another thing that could happen is if we started to manage diurnal fluctuations to actually occur within a day at 12-hour or 24-hour cycles, a stage fluctuation of 1 to 2 feet could change the pore pressure in the banks, leading to large-scale failure of channel banks as the pore pressures changes basically create a rapid drop that leads to bank failure. I'm not proposing we go down that route, but it is something that just something like diurnal fluctuations in the peak could create a disturbance that has an effect that's positive for encroachment and has large scale morphological changes, but may be really uncomfortable for people who live next to the river. Inundation, our initial data suggested that it took more than 120 days of inundating plants to kill them. However, they were mature plants that we were looking at. It is possible that late season increases in flow of longer durations could kill the plants. However, we don't have any monitoring data to really look at that directly. And then finally, causing flows to recede so quickly that you desiccate them. In our initial studies, we found that that was about 5% of the plants. However, depending on how that was addressed and the rates at which recession occurred, we might be able to increase that to a higher number, but it probably is going to be prohibitive from a recession rate standpoint. So if we come back to what our initial hypotheses were, basically, their initial hypotheses are untestable because we didn't do the core sediment augmentation the way we originally visualized in the volumes and water year types that we thought. It didn't come about where the channel bed got finer. And certainly in the period of record that we have from 2005, we only have 1 3-year period to look at in terms of dry years in a row. And so this was not, we basically rejected both hypotheses as being a valuable tool for us to manage. And we labeled them as untestable as they are right now. So we came up with 2 hypotheses, or 1 hypothesis, and that is a modification of the original, which basically, if we have the peaks at the current frequency envisioned, they are not going to be capable of managing it. If they are happening at the frequency or greater than the frequency that was envisioned, they will manage it. We did not include a 1-2 punch hypotheses where you have two lower than, or the first one being lower than capable of managing the age class 3 years or whatever the target is, and then the next are having a flow and seeing the encroachment effect managed, because it's only occurred once in the period of time that we've been sampling, and we would need to have a structured sampling in order to be able to look at that more closely. So the synthesis report made several recommendations. One of them has to do with this idea of getting everybody on the same page, or at least some type of statement about what we believe is an achievable channel pattern. And some of this work has been done. However, there's a very long discussion about some of the strengths and weaknesses with the work that's been done in the synthesis. I believe there's a lot of work that is still to be done here. But the reason for trying to define an achievable channel pattern helps us to manage people's expectations relative to the long-term evolution of the river. We proposed revised encroachment hypotheses. This could stand to do some more work, particularly as it relates to two flood peaks in a row having a management outcome that wasn't originally anticipated. It's been since 2004 that anybody's gone out and meaningfully quantified the berm condition river-wide. It's probably would be a good idea to do that just to see how far we've actually gotten. Certainly, our conceptual model for how coarse sediment was going to influence both the river and encroachment has changed. And there's some work here that needs to be done in terms of updating our management plan to reflect what our current thought is. Certainly there's some good work that's got in there between GMA and Dave Guyman's work, but I don't think that there's actually, that's made it into a formal management plan. The exposed gravel bar census is an easy thing to do. Seems like people care about gravel bars, so quantifying the number, whether they're growing or decreasing. I'm now getting into a little bit of the physical process discussions from last week. This may not be the right metric. However, it's easy to take. It's really quick, and it's useful from a comparison standpoint year to year. This idea risk to inform annual flow release timing. As of right now, we're just using flood peaks as a surrogate for assuming that encroachment or seedlings are being managed. There's no formal monitoring going on here. That's probably okay as long as we're not interested in things like the 2 peaks in a row managing seedlings. And then finally, I think it would be very valuable for us to experiment with summer base flows to increase variability there. I know there's a lot of reasons from temperature management that we wouldn't want to do that. However, this is really where we have the greatest amount to learn, and it's probably from a water use standpoint, the lowest amount of water use to create the greatest amount of management. So that's my quick shotgun through the encroachment synthesis. There's a lot of discussion that I didn't cover here. So I encourage you all to read it. Both the phenology as well as the encroachment synthesis can be downloaded off of the program's ODP. Please feel free to communicate with me. I'm happy to discuss this at any level you're interested in. And so I'm done with this presentation.
All right, thanks,
open for
John.
questions.
Yeah, unfortunately, the RCD has to go use their Zoom account for a different session. So if you do have questions, go ahead and reach out to John directly. Otherwise, we're going to conclude for today. Our next session will be on Thursday, December 2nd at 1 p.m. Thanks a lot, everyone. Thanks for Scott and John for presenting, and hopefully we'll see you then.
Okay. Thanks a lot for having us. Have a great afternoon, everybody.